I've been this class is stressing me out. Like my Cal 1, my Cal 2, I can go in there and in my sleep teach Cal 1 and Cal 2. This class just always stresses me out. It's not you. It's the class. It's the class itself. It's the material. It's the material. It just kind of stresses me out because I don't know. I just feel like the last few days we've been just kind of not on a solid path. You know, just kind of like all over the place. And it's because I just so want you to understand the unit circle that I'm not caring about what the book is saying. I'm caring about what I think I know you need to know. Does that make sense? As opposed to trying to follow the format of the book. And so I have a real big issue with like the online homework system. Like we're kind of required to have you do the homework online, but if it were my choice, we wouldn't do it at all. I don't even like the way they phrase all the questions. So with that said, today I'm going to just refocus us on what the important concepts are because we have a test next Thursday, right? And so I have two old exams that I'm going to share with you all. One of them is an exam 1 and the other one is an exam 2. And there's some overlap there. I'm going to tell you what problems to look at, but I'm going to share that with you probably in the next 24 hours, 48 hours. And that way you can get an idea of the types of things that I'm going to ask you on the test. The things that are important for me to ask you. And like that way you can not be thinking so much about the homework and focusing on what those exams say. Does that make sense? All right, so let's get refocused here today on the main concept. And what I'm doing today is kind of finishing up. There's one little thing in 7.5 that I need to talk about. I'm going to get into 7.6. Here you go, sir. I'm going to get into 7.6, graphing sine and cosine, which we started last time and we actually did. And then I'm going to get into 7.7, which is graphing tangent, cotangent, secant, cosecant, cotangent, all the others, all right? So let's start now with 7.5, well, finish 7.5. 7.5 is when we were talking about the unit circle and using the unit circle as the approach for the trig functions, right? The unit circle. And I obviously have made sure you understand the unit circle, right? So everybody have your unit circle out with you. And if you don't have it memorized, just have it readily available. Probably make today easier for you. So there's these two concepts in this section that I did not talk about that I just want to make sure you're clear on. It's the idea of even functions versus odd functions. This is a concept from college algebra. So in college algebra, you should have been, I guess your instructor should have defined what an even and an odd function is. So I'm going to just put the definitions up there, and then we're going to talk about specifically the sine and cosine functions, and ask ourselves, are they even, are they odd? What's the case? So in terms of even function, the definition of an even function is this: that when you take the function and you plug in some value x, right? So you take some function, you plug in some value x, whatever you plug in, if you get the same answer when you plug in that negative value, but instead of being x, you plug in the opposite, negative x, if those two things are equal, then you have an even function. All right? So that's the definition of what it means to be an even function. Let me give you an example. Example of an even function. F of x equals x squared. That's an example of an even function. The reason it's even is because if I plug in, let's just plug in a random value. How about 3? Do I get the same answer if I plug in negative 3? What do you think? If I plug 3 into this, what do I get? 9. If I plug in negative 3, I also get 9, right? And if that works for every number, then we call it an even function. Make sense? So in this case, it is true, right? This isn't a question. This is true. And that works for all values of x. If you wanted to show that more algebraically, you would do this. Imagine plugging in x, right? If you plug in x, let me do it this way. I don't want to use that part of the board. I'll just go right here. So if I'm trying to check if this is true, then I could write, let's see, f of x is x squared. The question is x squared equal to, now plug in negative x into this, and that would look like this, negative x squared. Are these two equal to one another or not? So if you take some number and square it, do you get the same thing as if you take that negative and square it? Yes, because if you square this, the negative times negative is positive. So yes, this indeed turns out to be x squared is x squared, which is true. Now, odd functions work a little different. Odd functions, what you need to be odd is this. That's even, right? That's what's over there. The only difference between even and odd is this. Not that these are equal, almost. This has to be negative. Okay, so plugging in a value into this and then making it negative will match what you get when you plug a negative into the function. Let me show you an example. What if I give you the function f of x equals x cubed? Well, so let's just pick a value. If I plug in, what do you want me to plug in? 2? Plug in 2? Okay, if I plug 2 into this function, okay, and then make it negative, so I'm plugging 2 in and making it negative, the question is that equal to plugging negative 2 into the function? Is it or not? Let's check it. If I plug 2 in, what's 2 cubed? 8, so I get negative 8, and is that equal to negative 2 cubed? Well, negative 2 cubed means negative 2 times negative 2 times negative 2, and that would also give you negative 8, wouldn't it? Negative times negative times negative gives you negative. So these are the same. Now, it's easy on polynomial functions to tell whether or not they're even or odd because you can just look at the power. If that's odd, then it's an odd function. If that's even, then it's an even function. So if you did x to the 4th, that would be even. If you did x to the 5th, that would be odd. The question is, the sine and cosine functions, are they even or odd? And I should mention, when it comes to functions, you can be even, you can be odd, or you can be neither. It is possible that you have a function that this doesn't hold for either way. Okay, so it's not one or the other. It's 3 possibilities, either even, odd, or neither. So the question is cosine or sine even or odd? So let's look at it. Let's look at the cosine function. And I'm going to use theta instead of x because I think it might be a little easier for us right now to do that. Think back to your unit circle. Okay. If I go somewhere, anywhere on this unit circle, doesn't matter where it is, right? And I pick some theta here. Let's look at what cosine of that angle is. So what's cosine of that angle? Which of these coordinates is it? The x coordinate, right? The cosine is the x coordinate, right? So whatever this is, this angle right here, whatever this x coordinate is, that's what cosine of that angle is. Right? Now, what if instead of going theta, I go negative theta? So I go backwards that same amount. Negative theta. Y'all still with me? What would cosine of that negative angle be? So whatever I was here, right? Cosine of that angle is the x coordinate. If I go rotate negative theta, cosine of negative theta should be what? This x coordinate here, right? And aren't these two x coordinates the same? They're the same x coordinates, aren't they? How much we go out is the same whether or not we go up or backwards, right? So in other words, these two are equal to one another, aren't they? If this is x and this is x, then we have that cosine of theta is equal to cosine of negative theta. So what type of function is this? Even, right? Because even said if you plug in x, you get the same thing as when you plug in negative x. That's what it means to be even, and that's exactly what we have here. Understand? So cosine is an even function. How would that be useful to us? What if I asked you, hey, what's cosine of negative pi over 4? Well, because this is an even function, this is the same as cosine of pi over 4, isn't it? It doesn't matter with the cosine function, it doesn't matter if you plug in a negative or a positive, you get the same answer. So if you don't know what cosine of negative pi over 4 is, which you should know, but if you didn't, then maybe you know what this is, right? So does everyone know where pi over 4 is?
Root 2 over 2.
And then the x-coordinate would be root 2 over 2, right? So this is root 2 over 2. All right, let's see if we can't. So at the end of this, cosine is an even function, all right? That's the takeaway. Let's try this for sine. Sine's a little trickier. More tricky? Trickier? Where's my English people? How about more trickier? That sounds like the worst mistake, right? All right, so what about this? Ooh, that's a pretty good circle. All right, so I'm going to do an angle, right? Here we go. Just making up an angle. I'm going to call that theta. What is sine of theta? It's the y-coordinate, isn't it? So whatever this y value is that's what sine of theta is, right? So sine of theta is equal to that y-coordinate. So we're talking about like this distance from here to here, right? That's the y-coordinate. That's what sine of theta is. Now let's look at sine of negative theta. Negative theta is down here, right? And now we take the y-coordinate here, don't we? This marker sucks. So what would sine of negative theta be? Is it y? No, it's not this distance, right? It's not the same y-coordinate. But it is the same magnitude, isn't it? It's just down here instead of up. So this would be a negative y value, wouldn't it? So it's basically that answer, right? If this is y, sine of negative theta is actually negative y, right? It's the opposite. Opposite in sine. So can we say that these two are equal to one another? No, right? We can say they're off by a sign, though, right? Whatever the answer is, it's off by a sign. Not a sine function, off by a sign, like plus or minus sign, right? So that is what it means to be odd, right? Because odd said this. That's what it means to be even, right? To be odd means not, this isn't the same. Put a negative here, that means they're off by a sign. And that's exactly what we have here. So the sine function is an odd function. I hope that makes sense. Yes or no? I'll just show you over here. What would sine of negative pi over 4 be? Well, according to this thing here, this should be not sine of pi over 4, but what? Negative, right? If you want to change this angle to a positive, then you have to put a negative out front. And so, do we know what sine of pi over 4 is? Root 2 over 2, but we need to put a negative in front. So, negative root 2 over 2. Okay, that's all I needed to just touch on in the section 7.5. Is just this idea of even and odd, and that cosine is an even function and sine is an odd function. All right? Yes?
What about tangents?
Okay, good question. What do you think? We can figure it out. Let's figure it out. We can do it without even referencing anything. Let's see if we can figure it out. Let's just go back to this right here. If I say theta is here, and I look at the x and y coordinate, what is tangent of theta? It's y over x, right? It's y divided by x. Okay. Now come down here to negative theta, right? Negative theta. Tangent of negative theta. So look at this point down here. Are the x-coordinates the same? At this point, the x-coordinates are the same, aren't they? So when I do y over x, that x is the same. But what about the y? It's negative, so it's opposite, isn't it? So whatever this distance is, this is going to be negative. Whatever that distance is, y, this will be the opposite. So are these two the same? Are they off by a sign? Yes, so they are. It is an odd function. So maybe your next question is, what about secant and cosecant and cotangent, right? Okay, so cosecant is the reciprocal of what? Cosecant is the reciprocal of sine. So what was sine, even or odd? Sine? Sine is odd, so cosecant is odd. Whatever sine is, its reciprocal inherits the same property. So cosecant would be odd, secant would be even, and cotangent would be odd because it's the reciprocal of tangent. These properties will come into play later, all right? Honestly, if you're doing a problem like this, this is not the type of problem where you would use the even and odd property to solve a problem. In your homework, they ask you to do that. If I'm doing this problem right here, let me tell you, if I'm doing this problem, okay, me, what I do is this. Mentally, I'm saying, where's negative pi over 4? Right there. And then I know on my unit circle that I'm looking for the y coordinate because that's sine, right? And then I know that that's negative root 2 over 2. How do I know that? Because I got 100 on my quiz, right? So the answer to this is negative root 2 over 2, which is what I just showed on the board, right? These properties of even and odd will come up later when we're trying to solve equations involving trigonometric functions. They'll be useful. And then we're trying to do identities and things like that. Okay, have I addressed all the questions? Yes? All right, so now we're going to move into the next section 7.6, which we started last time. We want to be able to, our goal here, let me tell you what the ultimate goal is, all right, for this section. The goal of this section to sketch y equals some number in front of sine and inside sine some number omega, not t, sorry, x. I want to be able to graph any function that looks like this. And I want us to be able to graph any function where it's a number a in front of cosine with omega in front of x. So specific examples. I want you to be able to do something like sketch y equals negative 3 sine of 5x. I want you to be able to sketch that, draw it for me. That's the goal of this section. Or like something like this, I could do y equals, let's say, how about we do a fraction? 1/4 cosine of 1/2 x. So if I hand you a sine function that's of this form, or a cosine function of this form, we need to be able to draw it by hand. That's the goal, all right? So how are we going to do it? To do this, we have to have a basic understanding. So to do this, we must understand what y equals sine x looks like and y equals cosine x. We need to understand what these look like. So you have to have a very, very good, clear understanding of what the standard sine function looks like and what the standard cosine function looks like. Then these are just some sort of tweaks and adaptations of it, stretching and compressing and moving things around, flipping. But you have to understand what these look like before you can do anything. So last class we talked about these, right? And I graphed them over there. The main characteristics of the sine function is that it completes one period between 0 and where? 2 pi, right? It's going to go through one cycle. There's here are 2 points, right? 0 and 2 pi are 2 important points on our sine function. There are 3 others that we need to be familiar with. The halfway point, which is pi, and then halfway between 0 and pi, which is pi over 2, and then over here, halfway between here and here is 3 pi over 2. Bless you. Those are the 5 important points on a sine function. There's 5 important points. For all sine functions, all standard sine functions, when you graph them, the 2 endpoints and the middle point are x-intercepts of the graph. So when we draw this, our sine function will go through here, here, and here. Do y'all know where that's coming from? What's sine of 0? 0 degrees, the y-coordinate. Okay, how about at pi? Y-coordinate over there, 0. Okay, what about at 2 pi? Y-coordinate, 0. Okay, that's why we have zeros there, right? Now, what about at pi over 2? 1. So all standard sine functions will have an amplitude of 1. We talked about amplitude is that number in front, the absolute value of it. And then what about 3 pi over 2? Negative 1, right? Because we're down here, we're looking at the y-coordinate. So you come down 1 like that, negative 1. And then what we do is we connect these together with a nice curve like this. And that's what I showed you last class, right? Okay. Now, you have to remember, this goes on forever, right? It just repeats itself, right? This way. And it repeats itself backwards, the same thing, right? We're going to need that. In order to do this, we're going to need this, all right? Let's look at that and compare that to the cosine. So for cosine, we still have the 5 important points. It completes a full period between 0 and 2 pi. Halfway is pi. Halfway there is pi over 2. And halfway here is 3 pi over 2. What's different, though? Where are the x-intercepts on the cosine function? So where is cosine 0? At what angles? Where is it? Pi over 2, right? Cosine is the x-coordinate, right? So I'm asking you, where's the x-coordinate 0? Here, right? Pi over 2. So we actually have an x-intercept here, right? And then also where? 3 pi over 2, okay. Those are where the 2 x-intercepts are on cosine. What about at 0? What's cosine of 0? 1, right? Cosine's the x-coordinate. So when I'm here, the x-coordinate there is 1. So that's a point on my graph. What about at pi? Pi is there. What's my x-coordinate over there? What is it? Negative 1. And then what about at 2 pi? What's my x-coordinate? 1. And then what it looks like is, like that. That's what a cosine function looks like between 0 and pi. They're different, right? They look a little different. But if we were to continue this, right? They're going to look exactly the same, just like a little shift. They're just shifted over. If you shift this over a little bit, you would have cosine. We'll talk more about that later, but when we talk about phase shift. All right. So I claim that in order to achieve our goal here today of sketching a sine or cosine function, we must first have a complete understanding that all basic sine functions have 5 important points. You have x-intercepts at the 2 ends and in the middle, and that at these 2 points you have peaks and valleys. Over here it's a little different. On cosine you have 2 x-intercepts at the quarter way and 3/4 of the way through, and that you have the peaks and valleys are going to occur at the ends or in the middle. Understand the difference? So how do we use that to achieve this. So here's what we do. I'm going to start with that problem right there. So we are now going to sketch. This is an example. We're going to sketch y equals -3 sine of 5x. And the whole idea here is to try and be able to do this quickly. All right? Like we want to be able to like get this graph sketched out. Okay? Sketched. Doesn't need to be perfect, just needs to be a good representation of what's happening. All right, so what I'm going to do first is I'm going to just recognize that in the front I have a -3. That tells me two things. First thing it tells me is that my amplitude, we talked about last class, right, is always positive. So it's the absolute value of that number, which is 3. And we said amplitude is that distance from the x-axis to the highest point, right? So that distance should be 3 for us. And then it should go down 3 as well. So our graph should go up 3 and down 3. The next thing is the fact that there's a negative in front. You see that negative in front right there? That negative in front tells me that when I draw this, I should expect to not see this picture, but to see that flipped over the x-axis. It's a reflection. Whenever you put a negative in front of a function, it flips it over. So I'm just going to kind of note that. The fact that I have -3, that tells me I should expect not that picture, but I should expect that picture, right? That's what I should expect instead, right? Not this. Bring that little hump to the bottom, bring that hump up, and then you get something like that, right? So it's a reflection over x. All right, that's how I'm starting. I'm just kind of saying, all right, this is my amplitude, and I should expect to see it flipped over. Now, the next step. Any questions? The next thing is we're going to establish what are our 5 points, right? Because here on a standard graph, it's 0, pi over 2, pi, 3 pi over 2, and 2 pi on a standard sine function. So the way that we translate that over to this is as follows, and you're going to do this for every single sine function you ever try and graph. You're going to take the inside of this function. What did I call that last class? That has a name. The thing that's inside the trig function. The argument. Good. The argument of the function, what I'm going to do is I'm going to set it equal to all 5 of these important values. I want to know, when does 5x give me a 0? When does 5x give me pi over 2? When does 5x give me pi? When does 5x give me 3 pi over 2? And when does 5x give me 2 pi? It's a little tedious, but this is the way to do it, all right? So I'm now going to set 5x equal to 0. 5x equal to pi over 2. 5x equal to pi. 5x equal to 3 pi over 2. And 5x equal to 2 pi. See, what I'm trying to do here is I'm saying on this graph, what x value do I have to plug in to make that basically turn into a 0? Because if this is a 0, I know sine of 0 is 0. And if I say, what x do I plug in to get pi over 2, then basically I know that if this is pi over 2, I know sine of pi over 2 is 1, right? So I'm just trying to figure out where these critical things are happening. And I believe the book calls this something, it's like the point method or something like that. Hold on, what do they call it? I don't care. They call it the 5-point method or something. I'm just saying set the argument equal to those 5 important points and then solve each of these. So solve that for x. What do you get? Divide both sides by 5, you get 0, right? So x is 0. Okay, solve that for x. Divide both sides by 5. What do you get? Pi over 10, right? Pi over 10. X pi over 10. All right, here to here. Pi over 5. Next one, 3 pi over 10. And the last one, 2 pi over 5. All we're doing is dividing both sides of the equation by 5. Or if you don't like that, we're multiplying both sides by 1/5. You get those new, these are our 5 new points. These points live on my graph, okay? These are the important points that are on my graph. They're not these anymore. They're those, all right? So now I'm ready to start drawing my graph. I'm going to erase this part. I'll leave the cosine up for when we do the cosine one. So what I know is this. No, I'm not using red. I know that I have an amplitude of 3, so I know this is 3 and that's negative 3, right? I know that much. I know that I'm going to have this sine graph. It's going to start at 0 and end at 2 pi over 5. So it's going to start at 0 and end over here at 2 pi over 5. And then these 5 points are exactly what they were on the other graph. The one in the middle, right? This was the one in the middle on the other graph. That's the middle point here. This is pi over 5. This quarter mark is this one, pi over 10. And this 3/4 mark is this one, 3 pi over 10. You understand what I'm doing? We've basically translated our graph or our function onto a new axis, right? Now what? What do we know about the sine function? Where are the x-intercepts on the sine function? Where do they occur? 0, pi, and 2 pi, right? But that was the starting point, the middle point, and the end point, right? So I know that my graph, because this is a sine curve, starts here, has an x-intercept here, here, and here. Okay, I know that much. Because it's a sine curve. All sine curves have x-intercepts at the ends and in the middle of your period. And now, what about at the quarter mark? Isn't it supposed to be up here? But remember, it's supposed to be reflected, right? So I'm actually going to just go here and go down to negative 3. And then on this one, I'm going to go up. And then I'm going to draw my curve, and I'm done. Questions? I erased this. Oops. It's all right, I'll do it over here. Sine x, right, has those 3 x-intercepts. And then on cosine, it's all right, what if I wanted you to draw me one more period of this? What if I wanted one more period? You would have to extend your x-axis out, wouldn't you? Now here comes a slightly tricky part. How are you going to figure out what these marks are? Okay, so how though? How would I mean, I know that I have another period. It's going to go like here. I'm going to have a halfway point,